Please welcome, from the Scripps Institution of Oceanography, University of California, San Diego, our moderator Lisa Taux.
Thank you. My name is Lisa Taux. I'm the chair of the Publications Committee. And today we're going to celebrate our past and inspire the future. Over the last century, we've figured out a lot of stuff. The universe is expanding. We know the age of the Earth. We have a much better understanding of how it works and its history, from continental drift to plate tectonics. We're exploring the solar system, really cool. And we discovered glacial cycles and increasingly understand their controls. And we have a much better understanding of the role of humans in climate change. And that's just a start. We have a lot to do. Over the past year, AGU journals have been publishing a series of papers that celebrate the past, but also highlight major questions and challenges that are ripe for pursuing in the future, in the coming decades. So today, we're going to hear short summaries by about a dozen authors, plus some insights from the science communications and education community. This is, of course, only a small selection focusing on those with significant societal impact. So check out the full collection online and stay tuned for more as they get published in the coming months. So let's get started.
Good afternoon. I'm Mark Peterson. I am at the U.S. Geological Survey, and I work on the hazard models for the United States. Today I'm going to talk about the probabilistic seismic hazard analysis at regional and national scales, state of the art, and the future challenges. How do I advance this? Anybody know how to?
If it's this, is there a...
There's this.
This.
Did it advance? Okay, that.
Oh, sorry.
That's good right there. Is it? How do I advance it again?
Keep pushing this green button.
I didn't put that.
That green one there.
Okay, perfect. Thank you. So the lead author is Matt Gerstenberger. He was not able to be here today, and so I'm taking his place. I'm one of the co-authors. But we have a truly international group of scientists that are working on these national seismic hazard models for different countries across the world, and I want to recognize all those and their different organizations. I want to begin by saying that these national seismic hazard models are very important for society because what we're trying to do is estimate where future earthquakes are going to occur, how often those earthquakes occur, how big those earthquakes will be, and how strong the ground will shake. Forecasting is very difficult, and so it's a very difficult job for us to do that, but we need that in order to make engineering buildings that don't fall down in earthquakes. We just released our national hazard map for the US yesterday, and so you might read a little bit about that. These are some of the different models that have been developed across the country, or across the globe. And you can see that they differ in scale. These are all somewhat similar to each other. The blue and the green areas are typically cratonic or extended margin regions where the earthquakes are more rare, and it's difficult to communicate with people exactly what those earthquakes are and how often they're going to occur. We also have earthquakes that are very, very common in places like New Zealand, Italy, the west coast of the US, Japan and Taiwan. They have lots of earthquakes. People are worried about those. They need to consider those in building codes. So just in summary, there were 5 major grand challenges that people would like to talk about. The first one is uncertainty in the source models, and that is where future earthquakes will occur and how often they occur and how big those earthquakes will be. There are uncertainties in our catalogs. We need to have homogeneous, good catalogs with good magnitudes. We need to understand better the complex ruptures that go into those models, and we need to use our new geodetic databases to be able to make better models. There are lots of other things on that list. We need to understand the uncertainties in the ground motions. So we look at we collect all this data around the globe, trying to understand how we can process it so it's uniform and so that we can understand what those shaking levels are. And that's one of our big challenges. And then trying to understand the site response associated with those is also a critical feature. We need to understand the process. We need to make sure that our processes are clean and that we're using the best available science. So we need them to be transparent and reproducible. We need to be able to communicate these methods and understand the uncertainties, which are very large in earthquakes, and we need to understand that. Finally, we need to validate and test these models because they have such large societal value. They govern, in the US, they govern $1 trillion per year in building construction and insurance rates. So we want to make sure that they're tested adequately. And we want to really make sure that the end users understand what we're giving them and how we use that. So thank you very much for your time.
Good afternoon. I'm Michael Poland with the U.S. Geological Survey Volcano Science Center. I think one of the greatest challenges we face in volcanology is forecasting eruptions and their impacts, and we don't have to look really any further than the tragic events earlier this week at White Island, New Zealand to understand the importance. Now, many volcanologists have drawn parallels with weather forecasting as an example of how our field might evolve. Several decades ago, weather forecasts were basically just exercises in pattern recognition. Barometric pressure goes down, there's probably a storm coming. And this wasn't based on any special understanding of the atmosphere, rather it was based on experience. Well, through a lot more data assimilation, especially space-based data, and models of how the physics and chemistry of the atmosphere actually worked, it was possible to develop into probabilistic forecasts of weather. And this is where my co-author and colleague Kyle Anderson and I believe that volcanology could move into more probabilistic hazards-based scenarios that are based on more data and more data assimilation methods. The way we've been doing volcano forecasting for the most part up until this point is pattern recognition, just as was done in weather forecasting many, many years ago. On the left is a map or a plot of the distance across a thrust fault on the floor of Mount St. Helens crater in the 1980s. And based on a repeating pattern of shortening across that thrust fault, it was possible to make accurate predictions of when eruptions would occur. This was just based on watching this repeated pattern. The same is true in looking at geologic evidence. On the right is a photo of Pinatubo's eruption in 1991. Prior to Pinatubo reawakening earlier that year, there was no real knowledge of Pinatubo's eruptive activity. But a very hurried program of geologic mapping led to an understanding that Pinatubo erupts every 500 to 1,000 years or so. And when it did erupt, the eruptions were very, very big. They affected all sectors of the volcano. And guess what? It had been about 500 years since the last eruption. And that was the basis for a very successful forecast of Pinatubo in 1991. We're blessed with a huge number of precursors that usually precede volcanic eruptions. A small schematic of them is shown here. Everything from deep, long-period earthquakes from magmatic systems that are well below the surface up to the release of gas emissions prior to and accompanying eruptions. And many of these things can be tracked from space. For example, on the right is a radar interferogram showing deformation at Kilauea volcano in 2018. This information was actually available to the Hawaiian Volcano Observatory about a day and a half before lava actually reached the surface. We're really growing in the volume of data that we have to be able to monitor volcanic processes. Two other developments that are parallel are the availability now of artificial intelligence, machine learning type algorithms to get through this massive quantity of data, as well as physiochemical models that actually look at the basic physics of how volcanic eruptions work. And these are tools that can help us forecast. The typical framework for a forecast is something that looks like what you see on the right here, an event tree in which we ask questions, is the volcano restless or not, and then move through different nodes until we get to actual eruptive impacts. This is often populated by expert opinion and statistics. Basically, you get people in the room and ask them what they think. And we believe that we could ultimately move to something that's a bit more complex that looks like this. Still a framework that allows us to incorporate expert opinion and statistics, but we would also be able to include physiochemical models on just how much magma is beneath the surface, machine learning approaches to recognize restless volcanoes, and advancements in the quality and the quantity of monitoring data. And this kind of capability is going to help volcanologists better issue warnings of activity, importantly on societally relevant timeframes. Thank you.
Good afternoon. My name is Deborah Akira. I'm a data scientist at the University of Southern California Information Sciences Institute. And today I'm going to talk to you about a crowdsourced reporting standards for paleoclimate data. In order to put the current warming trend and projecting warming into context, we need to be able to look at its geological past. Each of the curves that you see on this figure aggregates many different records representing thousands of human hours, mostly done by early career scientists. In fact, it's been estimated that they can spend up to 80% of their time data wrangling. We should be able to do better. So how can we do better? With linkters, we thought that the path forward is through standardization. So the first question is, what is a standard? And really, we decided that it was 3 different things. The first one is that it is a data container to hold the data. The second is a vocabulary to describe the components of the container. And the last one is a set of reporting practices to decide which property should be in the container. And here I'm going to focus on this last one. We started the discussion back in 2016 an in-person workshop in Boulder, Colorado, before moving the discussion online through 2017 in order to broaden participation. In the end, we had 135 researchers from all over the globe who voted on 633 properties. So what did they vote on? They voted on decided whether or not the property is essential, without which we cannot reuse the data whatsoever, recommended to ensure maximum reuse of the data, or simply desired. And the idea here is to reduce the time to science. Since the data is already in a standard format, it can be easily integrated and used by other researchers. So the question is, how do we go from here? And essentially, there are 2 challenges to this. The first one is the technical challenge. And how do we lower the barrier to metadata archiving? And here we can actually call upon machine learning techniques such as recommender systems to help scientists archive their data. The second challenge is social, and we need to change the incentive structure around standards. First, we can actually create codes that help scientists get to their goals faster. The second lever goes through funding agencies, not only in terms of funding crowdsourcing approach to standardization, but also in implementing the standard and recommending the standard for use through data management plan. And this needs to go beyond the US. The next lever is through editor and publisher, who can also recommend the standards to the authors. And finally, it goes through professional societies who can help with crowdsourcing standards and also implementing them. And the idea is to make the data fair at the end. Thank you.
Good afternoon. My name is Jan Leenaerts. I'm from University of Colorado Boulder, and I want to bring you to the polar regions for the next 4 minutes and focus on ice sheets. Ice sheets lose mass, and that's why it's relevant, because they contribute to sea level rise. How do we know? Because we can observe it. We can observe it through the GRACE gravimetry satellites, and you can see both ice sheets becoming redder and redder with time, which means that they're losing mass. Greenland on the left, Antarctica on the right. Note that this is not to scale. Antarctica is much, much, much larger than Greenland and contains up to 58 meters of sea level rise, while Greenland is only containing around 7. What is the same or similar between the 2 ice sheets that they're both losing mass? So the curve is going down, and the ice sheets are redder with time. So that's why we care about ice sheets, but we wonder why and how do these ice sheets lose mass? There are 2 main mechanisms by which the ice sheets lose mass. They can discharge ice into the ocean through ice calving, which you can see on the left, and they can melt ice and snow and transport that in liquid form from the ice sheets all the way to the ocean. That's what we call meltwater runoff. And meltwater runoff is one product of an entirety of processes that we refer to as surface mass balance. Surface mass balance, unlike discharge, is actually poorly constrained by observations because it's so complex. It's complex and it varies in time and space across the ice sheets. It's a result of many atmospheric and surface processes, and that's why we need to understand those processes one by one and as one entirety better. So we know that in the last decade we've done a lot of progress. We've made a lot of progress. We've installed new generation weather stations on ice sheets. We can use GPSs and altimetry from space to observe the changes in surface height on ice sheets, which is really exciting. And last but not least, we have new instrumental techniques, observational techniques, to directly measure surface mass balance in situ from the field. And recently, also due to the new observations, we can actually model it well. We have regional climate models that in the last decade have actually come to the point where we know that they model the surface mass balance on ice sheets pretty well. So two challenges I want to highlight before I end. So I mentioned altimetry as a great way of measuring surface height changes, but we need to know what these surface height changes represent. Is it fresh snow? Is it old snow? Or is it ice? So we need to know density, and that's kind of the product that relates surface height changes to mass changes. And secondly, we need to understand the interactions between the ice sheets that lose mass and the rest of the climate system. So to do that, we need Earth system models that by themselves need to be able to represent surface mass balance on ice sheets more correctly. So in conclusion, surface mass balance plays a role directly and indirectly in ice sheet mass loss. We've made great progress in observing and modeling ice sheet mass balance, and we need to work more on improving and constraining surface density on ice sheets and to develop Earth system models. Thank you.
So hi, I'm Chris Little. I work at Atmospheric and Environmental Research in Massachusetts, and I'm going to be talking very briefly about the challenge of sea level rise. So this paper and the talk is really a collaborative effort. Bob Kopp here on the left side is really the visionary, and he couldn't be here this afternoon, so I'll do my best to present it very quickly. And let's not forget about these two who are also participating. So I'm going to highlight two quick challenges, or significant challenges associated with sea level rise. There's really high societal vulnerability to changes in sea level. And a paper which recently came out that was presented here at this conference looked at the population, the global population subject to annual flooding. So that's not 1 in 100-year flooding, that's annual flooding. And 250 million people are within that zone today. And then, of course, if you add sea level rise on top of that, you increase that number substantially, to the point where you can double it depending on if you have a relatively high sea level rise scenario. But almost more importantly, that assumes no demographic changes. So we look around and we see people moving to the coast, moving to this high-risk area, and that's only going to intensify the problem going forward. Second main challenge is that both natural and human systems are characterized by a couple features which make the problem difficult. We're highly uncertain about some of the processes that are involved, especially over longer times into the future. There are irreversibility concerns. So once we lose something to inundation, we're not going to get it back. And then third, there are long time lags in both the natural and the human systems. So if we look quickly at the figure on the bottom, we can see that the amount of sea level rise that we see in the 20th century or 21st century is far less than what we're actually committed to going forward in 100 or 1,000 years. And then we can think about the infrastructure that we put in, how long the time lags are between when we put that in and when it goes out of use. And if we look backwards, in New Jersey, in Hurricane Sandy, 90% of the population, or PSE&G's customers, lost power during Hurricane Sandy, and half of the switching stations that were responsible for that were sited before 1911. So that's a long time in between when infrastructure goes in and when it might be vulnerable to sea level rise. So the paper that we generated is called Usable Science for Managing the Risks of Sea Level Rise. And the key point, or one of the key points that we make, is that sea level science is only useful if it integrates. And by that, and I'm going to focus on two areas here. The first is the different processes that are involved in sea level rise. We talked about surface mass balance of ice sheets, but we also have changes in the ocean, changes in land motion as well. And the second aspect that we need to integrate is human activities. So human activities are responsible for the emissions, which cause sea level rise. We modify the coastlines, which changes the risk. And then we make decisions based on the risk itself. And so those human activities need to be factored into sea level science to make it usable. We've made a lot of progress, particularly in bringing together the different physical processes that are responsible for flooding and sea level rise. We've closed historical sea level budgets at local and global levels. We're able to bring the terms together into probabilistic projections of coastal flood risk. We're developing new models which couple some of these components. We have economists who are doing data-driven analyses to find out how people respond to sea level change and how they respond to policies put in place to deal with sea level change. And all of this awareness about a grand challenge of sea level has led to a lot of interaction between scientists and decision makers. So going forward, I think I've learned a lot at this conference about new processes which we need to learn more about with respect to sea level, and also with respect to the interactions between these different components of sea level. We can continue to develop our coupled models, but I think we also need to keep in mind the fact that there will be significant amounts of uncertainty in long-term sea level rise projections, so we can work on assessing future sea level changes in the context of that deep uncertainty and communicating science to end users. We highlighted a couple decisions-first frameworks and flexible adaptation pathways in this paper. And then we also need to get political scientists and political economists in there and help us understand whether the adaptation plans that we're putting in place are equitable and the best ones possible. Thank you.
How aerosol particles form in the atmosphere. My name is Shan Huli from University of Alabama in Huntsville. These photos were taken by my colleague at Fudan University from the campus in Shanghai, China. One shows the view of city of Shanghai on the very normal fair air pollution condition, and the other shows the same view but on a very polluted haze day. The World Health Organization estimates approximately 4.6 million deaths each year directly caused by air pollution problems involving particulate matter. The problem here is how these particles form in the atmosphere. Aerosol particles either are emitted directly from various sources, such as volcanic eruption, dust, sea spray, or they can form from new particle formation processes. New particle formation has two steps. First, nucleation of clusters from gas phase molecules, and the second, the subsequent growth of these clusters to the aerosol particles larger than 3 nanometer. New particle formation is the source of number concentrations of atmospheric aerosols in the troposphere and the lower stratosphere. Global models estimate approximately 50% of cloud condensation nuclei are generated from new particle formation processes. For example, observations we made from our group in the Ozark forest shows that new particle formation can take place continuously over 5 or 7 days of consecutive days. And during this period, particles smaller than 10 nanometer can grow to hundreds of nanometer to act as cloud condensation nuclei. Epidemiology studies also show that ultrafine particles smaller than hundreds of nanometer, they have a much higher penetration and deposition efficiency in the lung than larger particles, so that they can have a higher toxicity on human health. The most important significant advances in our field is the molecular level of understanding of several new nucleation processes from the recent CERN cloud chamber experiments and other laboratory experiments. These studies highlight the importance of sulfuric acid, ammonia, amines, highly oxygenated organic molecules on new particle formation, as well as suppressing effects of NOx on new particle formation. Another important finding from atmospheric observation is that new particle formation actually can take place actually very frequently in extremely polluted Chinese megacities, such as in Beijing, where there are several hundreds microgram per cubic meter of PM 2.5, particulate matters smaller than 2.5. As a reference, the World Health Organization air quality guidelines recommend less than 10 microgram per cubic meter of PM 2.5 annual concentrations. These observations, however, cannot be explained by the current knowledge of the field that new particle formation cannot occur in the presence of high loadings of aerosol particles due to the scavenging of nucleation precursors and nucleated clusters. So this also poses a new challenge in the field. So what needs to be done? First, we need to understand the fundamental chemical mechanisms responsible for aerosol nucleation and growth under complex and diverse atmospheric conditions. We need to understand the effects of sulfur dioxide and NOx on new particle formation processes and the contribution of anthropogenic organic compounds on new particle formation processes. For example, what are the relative roles of biogenic versus anthropogenic volatile organic compounds on new particle formation? What are the relative roles of organic versus inorganic compounds on new particle formation? And what are the specific nucleation mechanisms dominating over land, ocean, forest, urban, rural, and high elevation sites, and the polar and tropical regions? And how to explain new particle formation occurring very frequently in extremely polluted urban cities, as well as absence of new particle formation in pristine Amazon rainforest. We also need to better parameterize new particle formation processes in the global models over a large range of chemical precursors, temperature, and humidity. Finally, understanding of new particle formation is important for development of new technologies and policies to mitigate global climate change, air pollution, and public health problems.
I'm the first in a series of 3 contributions, centennial contributions to the journal GeoHealth. I'm going to discuss the future of pollution identification and mitigation. I was helped along by a great team of co-authors who span the gamut of atmospheric and air scientists, water scientists, and soil scientists. And one of our main goals is to try to understand what separates us, the earth scientists, from the health scientists in terms of our data collection and translating that data between the 2 sectors. And the gap is pretty large. If you can think of it as a layer cake, that we understand quite well the environmental layer, and even to some extent the exposure, the transport layer of pollutants into bodies, whereas a lot of the health data is exactly that. It's stored in health repositories and are studied by public health experts. We want to collapse that sequence, and that's why GeoHealth was formed in the first place. One example of why this is such a difficult challenge comes from lead poisoning. Lead is a neurotoxin. Early exposure to this neurotoxin causes lifelong deficits in intelligence, memory, and risk aversion, so risky behavior. The problem is that lead is very heterogeneously distributed, and it is also in soils and dust. It's also heterogeneously distributed in human beings. This is a map that we produce of blood lead levels of children. Every orange and red mountain you see here in the city of Indianapolis is a poisoned kid. So rather than map poison kids a year in and year out, as one example, we need to collapse that distance between the health records and the environmental records. And I'm going to show you several case studies, modern case studies, that show, we think, at least the future pathway of how we're going to achieve that. One of them is the science at scale example from Bangladesh, where we're trying to use community-based sampling of geogenic arsenic in well water, and trying to help communities understand that just because one well is clean doesn't mean that the well about 4 houses over there is still clean. In fact, it can be quite dirty. So putting tools in communities' hands. Another one is biosensing pollution, whereby we use various biosensors, in this case bees and honey, to map out the spatial distribution of contaminants, whether they be heavy metals or any other number of things. We're taking advantage of the fact that we are now developing vast air quality networks of low-cost sensors that are pervasive. And these sensors allow people and communities to overcome air pollution issues by first identifying sources and then going to the sources and narrowing in on reducing that. Another example is our own work, where we've capitalized on the development of low-cost hyperspectral cameras and drones to be able to map the distribution of heavy metals in African cities from space, or from sky in this case. Finally, I think one of the things we really need to focus on is, as scientists, is to bridge the gap to community a lot better. So we've been working and launched this fall, mapmyenvironment.com. Don't look at it now because you have other talks to hear, but nevertheless, it's a citizen science effort, so we can encourage people to take samples of soil and dust or other things and analyze them at low or no cost to put the science of GeoHealth in the hands of citizens who need it. Thank you very much.
Hello, my name is Susan Glassmeyer, and I'm a research chemist with the U.S. Environmental Protection Agency. My colleagues and I were challenged to look at the future of contaminants of emerging concern. Contaminants of emerging concern, or CECs, is a catch-all group compensating a large swath of chemicals and microorganisms that are present in the water cycle. CECs you may know of are pharmaceuticals, PFAS, PFOA, Legionella, and mycobacteria. The term CECs has only been used for about 20 years, but the concept behind CECs has been going on ever since people drank a glass of water they realized they really probably shouldn't have. Back in the 1850s, John Snow, when he was removing pump handles trying to stop a cholera epidemic, he was dealing with CECs. Rachel Carson in the 1960s, when she was writing against DDT and how it affected birds, that was a CEC of her time. So today we're going to talk about the CECs of our time and what might be in the future. But before we went to the future, we wanted to look a bit at the past. On the left-hand side are a series of pie graphs charting the expanse of CEC data in the literature, from only 2 publications in 2002 in 2 journals to over 500 publications in 2017 in 125 different journals. The bar charts in the center also give 2 examples of why and how CEC research has expanded. The number of publications in these 20 journals increased by 7% per year over this 20-year period, but CEC research is increasing at a rate of 36% per year. Looking at pharmaceuticals and microplastics, you kind of see the evolution of compounds in these samples, where pharmaceuticals was one of the first CECs that was investigated, so there's a good 20 years of research now on these compounds. Microplastics has only been realized in the past decade that it's also a pollution problem. The pie charts on the right side, though, indicate how far we need to go. The little tiny green sections in each of the pies are the number of compounds in each group that we have data on or that it's been reported in the literature. So some of the flame retardants may be up to 30% recovery, or 30% of the compounds have been looked at, but pharmaceuticals right now, only less than 5% of the compounds have been reported in the literature. So to find out what the next compounds might be that are considered CECs, we're supporting a interdisciplinary integrated research efforts, as indicated by the Venn diagram on the left-hand side. We want to look for what CECs are present in samples, what health effects they may cause, and ideally, what can we do to mitigate these samples to protect both human and ecological health. And if we can design products to interact in that nexus between all 3 samples, that'd be ideal. But trying to get 2 is great enough. To illustrate this, I want to present some of my own data that we've collected the past several years. The colorful bar graph at the top is a set of sampling points from a stream reach where we're going upstream of our wastewater treatment plant. The tallest bars are the wastewater samples, and then progressively downstream into drinking water treatment. For this project, we looked for 236 contaminants of emerging concern, which is a pretty great number for environmental studies. But we didn't get the whole picture. On the bottom left-hand side, the bar graph is monitoring a glucocorticoid bioassay. Glucocorticoids are steroid hormones. You may know of them, like prednisone is an example of glucocorticoids. In this bioassay, we picked up activity in the wastewater treatment sample that was not present, or that cannot be accounted for by looking at the compounds we looked at individually. Likewise, on the bottom right, we did a metabolomics study. And in some of the downstream samples, we saw an increase in the metabolomic activity that's not captured by the compounds we looked for. To try to tease out a little bit better what's going on in these samples, we're doing non-targeted work, both looking for suspect screening, so glucocorticoids that we know might be there, as well as scanning the samples to try to get an idea of what compounds might be responsible for these health effects. We can also then do modeling to then predict compounds that we haven't looked for to see how they might also exist in these samples. But in the future, in terms of water management, there's going to be two different scenarios. Several of the speakers today have talked about the water surplus, that due to sea level rise or due to flooding, there might be impacts on the quality of water, particularly groundwater that might have wellheads being inundated by wastewater, or seawater intrusion into groundwaters. On the opposite side are locations that are impacted by droughts or increases in population, where they may be impacted by a water deficit. In these locations, they may need to find alternative water sources, including direct portable reuse. They may have their groundwater in that area be depleted, and they may have other limitations on their wastewater or their water quality in terms of distribution system pipe breaks and wildfires. In all these locations, we need to increase infrastructure, deal with the mitigating problems that could come, such as brines, increase energy, and most importantly, get stakeholder buyout. Thank you.
My name is Anta Jutla. I am Associate Professor of Environmental Engineering at University of Florida. And in the next 4 minutes, I'm going to talk about a topic that impacts us all, infectious diseases, which includes Zika, dengue, chikungunya, flu, and all kinds of waterborne diseases. So this is, it's not going forward. Oh, so this is the work that our team has done over last several years. So our team includes Dr. Rita Caldwell from University of Florida, Dr. Helen Nguyen from Illinois, Dr. Joanna Schisler, and Dr. Avinash Unikrishnan from Portland State University. I'm going to talk about one example of the existing knowledge that we have achieved over the last several years. And I'm going to then discuss the challenges that exist that the GeoHealth or geosciences community is going to face in next 100 years or more. And we need, how are we going to bridge those challenges and gaps? So over the last several years, we have done tremendous work on understanding the etiology of pathogens, but then how pathogens are linked to geosciences or geophysical processes, that's something that we are still trying to understand. So for us, a $1 billion question and a grand challenge is where is going to be the next pandemics? So that pandemics can be a waterborne pathogen-based disease outbreaks, or that could be a vector-borne disease outbreaks. So it's not a simple and straightforward question to answer. It includes various bits and pieces, various disciplines, and the knowledge from all those disciplines needs to be combined if we really have to holistically answer that question, that where is going to be the next pandemics, and then what is going to happen under changing climate. The figure on the bottom here shows a 2018 survey of words from the Google and social media that people have looked online. So as you can see that the diarrhea was the most searched word, followed by influenza, and in that year there was Zika, SARS, meningitis, cholera, measles, all kinds of stuff. So this is a slide that shows you all kinds of diseases that are present in different parts of the world. And while each disease needs to be thought individually, there is something that we as a geosciences community needs to understand and interact with public health communities. So I'm going to show you one quick example of the work that we recently did, and this is the prediction of cholera. So prediction of cholera, this was done for the first time on a near real-time basis in South Sudan in August of 2019. So this figure shows the red regions where the risk of cholera was very high, and we were able to pinpoint the exact locations where the population is actually at risk of this disease. And this was communicated to various NGOs and our end users. We were able to identify, or at least like probabilistically determine where are the water resources and probably what population needs to do in order to prevent the massive outbreak of this disease. So this is one of the examples, one of the successful examples that we have done over the last several years. And the way that we have done is that we have integrated the information and knowledge from sociology, microbiology, public health, and most importantly, geosciences, because the prediction of environmentally modulated pathogens needs to come from climate and hydrological processes, because that will give us the lead time to predict these diseases. So what's the future for us? We try to summarize it in this figure, that what is going to be the future and where do we stand in terms of prediction of these diseases. So here, there is a constant interaction between the geophysical processes and water ecological processes. There is a scale difference in geophysical processes, which is thousands of kilometers, and water ecological processes, which is basically on very kilometer or less scale. And then we have challenges. The challenges are the porous rectangles, the dotted rectangles, which basically creates these biothreats. If we can stop how the knowledge or how the information, if we can basically close the rectangles, the sociological determinants in civil infrastructure or pathogen survival or growth, then we should be able to predict the outbreaks of major pandemics. With this, thank you so much.
Good afternoon. I'd like to talk to you about subseasonal to seasonal prediction of weather and climate over the next 4 minutes. So I'm Andrew Robertson from Columbia University's International Research Institute for Climate and Society. And the photo next to mine is Frederic Vittard from the European Centre for Medium Range Weather Forecasts. And together we're leading a community initiative that's called S2S, Subseasonal to Seasonal Prediction. It's a joint project of the World Weather and the World Climate Research Programs. And in fact, WCRP just had its 40th anniversary at this AGU meeting. And this is a community effort, so you can see the steering group there of the S2S project. So on the left, you'll see a cartoon of weather forecast skill at the left. The x-axis runs days to months. And you can see that we have some good skill in weather, but it falls off rapidly as we lose the information in the initial conditions. And then on the seasonal timescale, we also have some reasonable skill in our seasonal outlooks that's actually used around the world for managing drought and other sectors. But the problem is there's a major gap in between. So the forecast range between weather forecast and seasonal outlook was long thought to be a predictability desert where there was little skill. So this is a major problem because many management decisions in agriculture, food security, water, disaster risk reduction fall into this kind of time range between 2 weeks in a season. For example, it takes the Red Cross, Red Crescent several weeks to get disaster relief supplies in place. So if they had a heads up of upcoming storm probabilities, that could be very useful to them. So why is this difficult? One of the reasons is that there are many sources, there are multiple sources of predictability of the weather and climate in this range. So if you think of seasonal climate, then El Nino Southern Oscillation is our main source. But in the subseasonal range, on that cartoon on the left, you can see many of these are depicted. The Madden-Julian Oscillation in convection, interactions with the ocean, land surface processes, the stratosphere. So it's a major research effort to identify and better understand these sources, and that's what the S2S project is doing. And how is this happening? It's really happening through this major new international collaboration between weather and forecasting centers. It's including national research programs, the academic and importantly user communities. We've been creating new databases and access to forecasts. And the one on the right is showing you just how complex that is in the modeling space as well, because one thing we need to do is really improve our forecasts. That involves observations, it involves how we initialize our models, it involves all the modeling components of climate, air-sea interaction, land-atmosphere interaction, and so forth. And then importantly, it involves how you actually post-process those forecasts. So I'll show one example here from last week. So there was a major super typhoon hit the Philippines, and this was actually forecasted quite well 3 weeks before. So from the 11 November forecast, we can see that there's a reasonably high strike probability. That's what's shown in the shading there, of 20 to 30%, even over 3 weeks ahead of time. So this is something that couldn't be done in the past, and it's a great example of how far we've come, but still we need to go further. So what needs to happen next? Forecasts that are really seamless across timescales, from daily weather to seasonal, from super forecasting centers to end users. This is the new frontier of forecasting. We need accelerated research to better understand those multiple sources of predictability, how they interact. We need improved forecasting systems. They're improving, but we need better ones. We need co-development, importantly, of forecast products by users and forecasters together. And this can happen really only through strong international collaboration and coordination. Thank you.
Good afternoon, everyone. My name is Elena Mondino from Uppsala University in Sweden. And today I will quickly go through our work, which was conducted by an interdisciplinary team of scientists led by Giuliano Di Baldassarre. The talk is going to be about how social hydrology can help address one of our societal grand challenges. Humanity is now facing a global water crisis. What we see in many regions of the world is an increase in flood risk, higher levels of water pollutions, and worsened water shortages. And these are all in addition to other phenomena which are much harder to catch on camera, such as, for example, groundwater depletion and water-related conflicts. So this crisis is generated by a complex web of interaction between social, technical, and physical factors, such as, for example, an increase in water demand, the construction of large dams, and the threat of anthropogenic climatic changes. This interplay between the hydrological and the societal sphere is precisely the focus of social hydrology, which aims at understanding and modeling these feedbacks deriving from these complex interactions. These feedbacks may eventually generate complex socio-hydrological phenomena, which are characterized by counterintuitive dynamics. So, for example, what happens in the supply and demand cycle is that we construct a new reservoir to increase the water supply, and these in turn may increase the water demand, therefore making water shortages even worse. In the rebound effect, what we see is that an increase in irrigation efficiency may translate into an even greater water use. While in the safe development paradox, what happens is that we build structural protection measures, such as levees, to protect communities from flooding, and this may in turn promote economic and urban development within the floodplains, therefore contributing to increased damages and losses in the case an extreme flooding event occurs. These phenomena can be seen as unintended consequences resulting from water management policies. But that besides contributing to the spreading of inequalities and to uneven distribution of costs and benefits, can also hinder the attainment of the water-related targets of the Sustainable Development Goals. So to this end, social hydrological modeling can help unravel the necessary trade-offs in reaching these targets. We can also use these models to compare different water management policies so that we can explore future possibilities and at the same time avoid these short-term fixes that can eventually backfire in the long run. So if you're interested in this topic and you want to know more, please have a look at our WRR Grand Challenges paper, and thank you very much for listening.
Good afternoon. I have the pleasure to take you from Earth all the way to space and the sun. I'm Noé Lugas from the University of New Hampshire and also the new editor-in-chief of Space Weather. And I'll talk to you about the impact of forecasting the impact of solar eruptions. And that's partially based on a Grand Challenge paper published in Space Weather before my time by Emilia Kilpua, myself, Leila Meis, and Manuela Temer on forecasting CMEs. First, to take on a common myth, on the left-hand side over there, you can see old Babylonian tablets. And in fact, the study of space weather and solar physics didn't really start in 15th or 16th century, like most of us read in book. There's been reports of sunspot and aurora sighting going all the way back from 6th century and 8th century BC in China and in present-day Iraq. But really what we call today space weather or solar connection started in 1859 with this gigantic active region you can see here in a hand-drawn figure passed in front of the Earth-facing side of the sun in September 1959, and one of these gigantic flares that can be seen with the naked eye very rarely occurred on September 1st. And about 1 day later, aurora sightings started to be experienced as far south as Cuba and Mexico, which is type of a once-in-a-100-year occurrence. And thanks to this, it was possible to make the connection between a solar event and its impact on Earth. And this is what we today call space weather, the influence of space environment and solar eruptions on aviation, radiation, satellite technology, but also on the ground technology due to currents flowing down into the ground. And really, when you talk about extreme event, those that have the potential to create a large-scale blackout that the National Academy of Science a few years ago said would cause tens of billions of dollars of potential damage are caused by solar eruptions. So what has changed since the mid-1800s? Quite a bit, in fact, thankfully, in terms of our understanding and technological readiness. In fact, we don't observe and sketch sunspots by hands anymore. We've built dedicated observatories starting in more than 100 years ago, and just next year, Dickest, which is a very big one over there, will have its first light in Hawaii. In parallel to that, we also have developed technology, the chronograph in the 1930s, which allows us to image these solar eruptions as they occur at the sun. Since the 1970s, we do this from space, and since about 2006 with Stereo, which is a movie running on the back here by Craig DeForest, we have actually the capability of imaging solar eruptions continuously as they propagate all the way from the sun to the Earth. That really has filled an enormous observational gap. Also, since 1957, the space age has begun, and since 1959, with the Soviet mission, one on the bottom here, we can actually measure solar wind directly. So we can measure the density, temperature, the magnetic field of these eruptions. Now, things to keep in mind is that only 4 years ago, with Discover, the one at the bottom, the shiny one at the bottom here, it's the first operational mission we have had. So all this time we have done science, but actually forecasting things require operational missions. And that's only started with Discover at L1, which gives us about a 1 hour warning of these things occurring. Of course, like most fields I've talked before, we have developed numerical simulations from very simplified one-dimensional ones in the 1970s to very advanced one in the 90s and right now, both in operational setting, but also for scientific endeavors throughout the globe in Europe, US, and Asia. So where are we, and what are we still missing? Well, since 1859, we have really developed kind of this understanding of this chain of connection of events from solar flares and its impact, auroras, but also on technology for simple events. But what we have to keep in mind is compared to all of my colleagues that spoke before me, we're very, very observational poor. In fact, for remotely observing this thing, we only have one spacecraft, the one I showed looking at from the L1 point. This should change in the near future. Hopefully, ESA will go with the L5 mission the next decade, operational mission, and then with more science mission in also the next decade and beyond. Now, for in situ measurements, those are actually measuring the density and magnetic field right here. We also have one buoy. Just think about doing all of your science with only one data point. That's us. And we know what we have to do. We have to go closer to the sun to get more advanced warning and put more buoy, more spacecraft. The question is how, where, and how many. In terms of how, NASA just funded a number of tech demonstration missions to go with smaller spacecraft, better propulsion, and better communication. In terms of the where and how many, that's really, I think, where we need a community to spend some money into science mission to really understand the morphological feature of these big solar eruptions, to understand how many spacecraft we need to go to be better forecasting in the future. Thank you.
All right, hi everybody. I'm Nicolene Weil from NASA's Goddard Space Flight Center. This is a grand challenge paper that I wrote with Joe Borofsky from Space Science Institute. And what we're trying to understand is solar wind physics. So NOAA just talked about the big space weather events that destroy our power grids and impact astronauts and our spacecraft. I'm talking about the sort of daily space weather, the smaller space weather, but the daily bombardment of plasma and magnetic field that interacts with our Earth and our magnetic field. That's me. All right, here we are looking at the sun in extreme ultraviolet. These are a series of images taken with Solar Dynamics Observatory. And what you can see is that our sun is extremely dynamic and structured every single day. Now, one of the big grand challenges from our perspective is understanding why the solar corona, the solar atmosphere, is so hot. It's 1 to 2 to 3 megakelvin when the solar photosphere below it is only 6,000 Kelvin. So it's hundreds of times hotter in the solar atmosphere, the corona. Why is it so hot? Well, we know the answer is the magnetic field. In fact, all of the dynamics and structuring that you're seeing in this movie is caused by the magnetic field. But we don't know exactly how that magnetic energy is dissipated. We don't know when it's dissipated, and we don't know where it's going to be dissipated. So that's number one. Here we're looking at a total solar eclipse image, so it's white light that you could see with your eye. It's electron density. This is the density of the solar corona as it expands outwards and fills our solar system. We call this the solar wind. Now again, the magnetic field is what is causing all of this structure that we're seeing in the solar corona. It's influencing how this corona expands outward and fills our solar system. Question 2 is, how does it get out though? The magnetic field in some cases is rooted to the sun on one end, and on the other end it extends outwards into space, so that plasma just flows along the magnetic field line. That's good. But the other kind of magnetic field has both ends rooted back in the sun, and you can see these loop-like structures here. How does that plasma get out? Well, actually it gets out by a process called magnetic reconnection. We're seeing that here in this movie. This is a zoom in on one of these closed magnetic fields, and it's interacting through magnetic reconnection with open fields next to it, releasing plasma out into the solar wind. So we've actually managed to capture this in certain situations. Now, this solar plasma, as it enters into the solar system, it reaches very fast speeds, 400, 500, 800 kilometers per second. Now we're looking at the solar wind as it streams away from the sun. So question 3 is, how did it get all that energy to get that fast? Again, the answer is the magnetic field, but was it waves? Was it turbulence? Was it magnetic reconnection? That's the third big question. We don't know how it got so fast. Also, you can see all of the structure. It evolves on the way to Earth. So we're talking about fundamental, universal physical processes at work throughout the entire universe that we're measuring directly at our sun. Things like turbulence, magnetic reconnection, wave-particle interactions. When those structures get to the Earth, this is the daily bombardment that interacts with Earth's magnetic field and interacts with Earth's radiation belts. So it's not the big space weather events, but it's the smaller ones that happen on a daily basis. So what are we going to do about it? Well, already, Parker Solar Probe has flown closer than any human-made object has ever gone before. That's what I'm showing on the left over here. Those are whisper images of Parker Solar Probe measuring the solar wind right after it comes off the sun. Solar Orbiter is going to be launched in February. That will take a different perspective of the sun. Punch is going to take global high-resolution, high-time spatial resolution images of this Sun-Earth connection. And then with DKIST, we can really zoom in and get some really detailed information about the sun. Oh, there's the Whisper movie going. So in conclusion, we need to understand how the solar atmosphere creates our space environment. Thank you.
I'm here to talk to you about the grand challenge of science communication. I'm Alexandra Witze. I'm a journalist who has covered the earth sciences for magazines and newspapers throughout my career. I want to talk about what to expect from communication in the next century. Science communication is a broad term. It encompasses whatever people hear about science after they leave school. It could be scientists like Katharine Hayhoe talking to a Rotary Club about climate. It could be filmmakers on board the Chikyu trying to document the challenges of deep sea drilling. I'm going to speak from the perspective of just one form of science communication, which is journalism. The hallmark of journalism is that it's done by professionals who independently report and analyze what's happening and put it in its full context. It often helps shape the stage for other science communication that comes after it, because journalistic pieces appear first and set the stage for the discussions to come. That's why they call it the first draft of history. But that landscape has been changing dramatically. You don't need me to tell you that more and more people are getting their information on mobile devices through a looser network of sources. They're not reading a newspaper in the morning and watching half an hour of Walter Cronkite at night. They're swimming in a sea of whatever their friends may have shared on Twitter or Instagram or Facebook or TikTok or YouTube or whatever. And this has enormous implications for how information about science reaches the public. It can be amplified and distorted much more easily. Bad stories can go viral. And because there's so many fragmented sources of information out there, people can easily find themselves isolated in a bubble with little idea about whether what they're hearing is valid or not. If you want to spend your time listening to earthquake prediction nonsense on YouTube, you can do that. And you probably won't have many tools to help assess what you're hearing. I believe that the most crucial challenge in this area is how to distinguish real information from bad information. It's clear that many readers have difficulty distinguishing between the two. Journalists and communicators have a major role to play in helping foster critical thinking. Well, how can we go about this? We can keep working to illuminate the process of science. In many types of stories and on many different types of platforms, journalism and science have a lot in common. We're both working to understand the world around us and to reveal what's happening in truthful and transparent ways. Journalists need to tell stories about science that help readers sort through how to evaluate that information. Now, I have to admit, I've spent much of my career deliberately not writing about bad information, not wanting to give it any oxygen in the media world. But now, sometimes I think that was a mistake. It's becoming clear that we have to confront this head on. I want to give a quick shout out to Vice, for instance, for their recent piece that debunks earthquake conspiracy theories. It doesn't just ignore bogus information that's out there, it provides valuable information for readers on why they shouldn't believe everything they hear on that channel. So where does that leave us for the future? There are still a lot of unknowns. Journalists are struggling to navigate this changing information landscape. We're also struggling to exist at all. Many forms of journalism are collapsing as newsrooms are hollowed out around the country and around the world. And even as we scramble to keep our jobs and keep up with the information overload, we also have to keep ahead of whatever dramatic news might be coming out of the scientific community, the sorts of trends and discoveries that we're all talking about here on this stage today. One question I ask scientists a lot is whether they're optimistic or pessimistic about where their field is going. And I have to say, it's a little hard not to be pessimistic about journalism these days. But after a quarter century of doing this job, one thing does stand out to me very clearly. The basic tools that underline both journalism and science, the ability to think critically, to wade through bad information, and to sort out what's true and what's right, are going to be more important than ever in this next century. So please, pay for your news, call that reporter back, and maybe, just maybe, we'll be able to fight back against this tsunami of misinformation that's threatening to swamp us all. Thank you.
Hello, my name is Kristen St. John. I'm the former editor of the Journal of Geoscience Education, and I'm a professor at James Madison University. I'd like to talk to you about geoscience education research, what it is, where we're going, and why it's important. And I'm going to start with why it's important, but first I'd like to acknowledge my collaborators. The efforts that we've been taking to capture, to understand the state of our current field and to chart a path forward has very much been a collaborative activity. So let's think about the value of geoscience education research. And really to do that, we have to think about geoscience education itself. And I'll start with a premise that building geoscience expertise and an earth science literate society both depend on high quality undergraduate education. And if we think about this, the exciting novel science that has been described here today, this is science that's going to be undertaken in part by you all in the room and colleagues that have been at this meeting, but in large part it's going to be tackled by your students, your current students and future students. So we need a very strong foundation in undergraduate education to support them, as well as to develop a literate society in science. Now, to have that high quality education, what we need is a convergence of two things. We need to converge both what we teach and how we teach it. And geoscience education is at that second limb there of how we teach. It's at the core of geoscience education research, or I'll abbreviate that as GER. Now, both of these fields should have a research foundation, and that's what we're trying to provide, and we're an evolving field. In fact, we've been described as an emerging field by the National Research Council, and more recently. Examples of how this is an emerging field include the number of papers that have been increasing through time. The fact that we have a disciplinary home with NAGT, the Division of Geoscience Education Research, and I'm very excited to see the directions that we can go now that AGU has an education section. In addition, we're seeing an increase in the number of graduate programs in geoscience education research. So our field is evolving, and it's evolving in a really important way. Okay. We have a strong foundation in doing scholarly work to approach our teaching, where there's reflective teaching practice, for example, in curriculum development. And a very nice example of this is the Cutting Edge Workshop program that maybe many of you have participated in and has had a significant impact in undergraduate education in the United States. What we're seeing, though, is growth of our field in a very important way. We're seeing an increase in social science theoretical models and methods integrated into geoscience education research. So the scope is expanding. And with that, we're positioned to test hypotheses and create generalizable results in a way that we have not been able to do in the past. So we want to be very strategic going forward in how we're going to do our research and how we can communicate it to the stakeholders. So how are we strategizing for going forward? And I want to just share two initiatives. One initiative in geoscience education research is increased focus on strength of evidence. And we've come at this in a very interesting way. We've tried to conceptualize strength of evidence by borrowing a model that's very fundamental to medicine, to evidence-based medicine. And I'll put up both of the models here. So recognize that these are pyramids. Evidence-based medicine and evidence-based teaching have some real parallels. If we think about this, both fields have large numbers of practitioners, your primary care physician and the educators that are in the classrooms that are probably grading exams right now. And those practitioners may not be doing the research themselves, but they need those research findings to make informed decisions. And they're making decisions that are affecting stakeholders. The stakeholders in medicine are all of us when we go see the doctor. The stakeholders in education are our students. So what we want to do in geoscience education research is ensure that we are moving across the levels of the strength of evidence pyramid. We have a strong foundation at its base, but we want to increase the number of studies, increase the complexity of the studies, and use more rigorous results so that we're moving farther up the strength of pyramid to have more generalizable findings then could feed back into practice. Now, another strategic approach is to think about what we should be focusing on for undergraduate geoscience education research. And like many of the other groups on the stage, our discipline has been looking at a grand challenges exercise, which we completed last year. This grand challenges exercise is produced a large-scale report. It's 155 pages, but you can also access it online with the QR code. And this is very much a community effort. We had 48 authors and an additional 150 reviewers or contributors in other ways. What we've done is identify 2 to 5 grand challenges across 10 interconnected research themes. And what I'll share with you here are what those themes are. These are areas where we think undergraduate research education can where research in undergraduate education can really help propel us forward to address important needs. So we would like to see future research that's targeted to improving how we teach fundamental concepts that are essential to the geosciences and across the geosciences, as well as fundamental skills. What does it take to become a geoscience expertise? We want to focus research on teaching in different settings. We teach in small classrooms and large, in the field and out, and to a wide range of populations. We also want to focus on integrating societal problems as a core link for reaching out to our students and helping them become better prepared to tackle societal problems, both as geoscience experts, but also as citizens. We also need to focus more attention on preparing future teachers so that the students that are coming into our programs are already better prepared. Another very important area of geoscience education research is access and success. We want to focus on access and success of underrepresented groups so that a career in the geosciences is inviting and supportive of all people. We need to focus research on how to better understand student motivations and interests to enhance their ability to learn and thrive. And lastly, we need to focus research on how our institutions, our professional societies, and professional development programs can better support instructors at all levels, because that will be the only way we can scale up the findings to improve undergraduate research in the geosciences. Thank you.
Thanks to all the speakers. This has been a great week at AGU. I know you've reconnected and made a lot of new friends and new connections. And we thought it'd be fun to share some details about the meeting that you might not know. So here's some numbers. How many people think we had more than 20,000 attendees? 25,000? Yeah. 28,000? Yep. And I don't know how many, but it's more than 28,000. We had 1,500 exhibitors and more than 400 press, including public information officers and reporters. How many think the number of countries is over 50? Everybody raise your hand. Yeah, over 90? Over 100? Yep, we had over 100 countries represented at this meeting. And there were 17,500 posters. And the Centennial Central sponsored 48 sessions. I hope you got to see some of them. There were more than 1,000 e-lightning talks. Oh my God. And AGU hosted more than 100 town halls. I'm sure you went to all of them. And 25 scientific workshops. This was all fueled by 4,500 gallons of coffee. And that's only just through yesterday. We haven't counted today's cups. But now we're going to hear from AGU Executive Director and CEO Chris McEntee. But before that, we're going to watch a short video. And I'm going to go away. Bye-bye.
The Earth is undergoing unprecedented change and transformation. Human activities are dramatically reshaping our oceans, continents, and ecosystems.
Organisms have three options on the planet. They can adapt, they can migrate, or they become extinct. For the majority of us, we're not going to be able to migrate off the planet. So we're going to have to learn to adapt, and we're going to have to figure out ways to address many of the issues that are impacting the planet. They're going to impact us, obviously.
Never has the role of the Earth and space scientist been so crucial, with so much at stake.
Your work is really critical. Hang in there. Tell your friends, tell your family, tell your communities about the work you do. Invite people into your labs. Help them understand what you do and how it fits into part of a bigger picture. Because if we don't, we will not leave that future that we aspire to leave to the generations to follow. It's really critical.
While the previous century was about unlocking the mysteries of our physical universe, the next will be about sustainability and providing solutions.
We are at the dawn of an incredible age of the marriage of technology and understanding planetary and Earth systems.
As scientists, you've made a career of unlocking nature's most tightly held secrets. Your work has made the seemingly impossible possible, time and time again. It's the remarkable achievements and breakthroughs of the last 100 years that gives the world hope and optimism for the future. You are the Earth and space scientists of AGU. This is your moment.
Please welcome AGU Executive Director and CEO, Christine McEntee.
It is a beautiful day. What an incredible, inspiring fall meeting. Before I begin my remarks, I want to make sure that I personally thank, on behalf of the entire AGU community, the chair of the Fall Meeting Program Committee, Denis Didier-Rousseau, and his incredible Fall Meeting Program Committee. All of the sections who went the extra mile over this past year to make sure that we had this incredible special additional Centennial Theater, and everyone else who contributed, including the amazing AGU staff, to making this such a successful and inspiring meeting. This has been a very special week for me, as this is my last time to address you as AGU's Executive Director and CEO. I am so grateful to have had the opportunity to talk with many of you throughout the week. It has been so exciting to hear about your science and the impact of this meeting on you, your research, and your careers. You have been energized by new ideas and renewed friendships, made new friends and connections, expanded your professional networks, learned something new, and shared your important work with our community and the world. Whether you're new to AGU's fall meeting or you're a seasoned participant, it is really great and fantastic to be among this community of scientists, especially this year, AGU's Centennial. This week, every session, discussion, and finding built upon the science and discoveries shared through AGU over the past 100 years. Let's think again about this past century of AGU. During the past 100 years, your work has been transformative about understanding our planet, the sun and space through your actions, innovations, and discoveries, such as plate tectonics in mid-ocean ridges, numerical weather forecasting, protecting water sources for environmental and human health, climate change and how we as humans are connected to Earth's delicately complex planetary system, the hole in the ozone layer, the extinction of the dinosaurs from a meteor impact, Van Allen radiation belts, life in extreme environments, observations of exoplanets, and many, many more. Quite an amazing 100 years. Things that have never before been imagined or thought have become our reality. Let's celebrate those achievements. Now you, the AGU community, you're on the cusp of AGU's next century. We, the global community of Earth and space scientists, have the opportunity and a responsibility to share what we've learned with as many people as possible, to lead with ethics and integrity, to work across borders and boundaries, to advance the next 100 years of awe-inspiring discoveries and address thorny scientific and societal challenges, as you just heard from our amazing speakers over this past hour. Those responsibilities are more essential in this age of disinformation and growing nationalism. Globally, we are seeing the devastating effects of what happens when science is doubted or flat out denied, despite numerous studies and research that clearly show the evidence and facts. Around the world, we are seeing populism and nationalism erect barriers to global science collaboration and exchange. At a time when science is being questioned and even dismissed by some, I want to remind you of an extremely important ally that overwhelmingly supports us and your important work, the public. Individuals from many countries are in awe of amazing discoveries, such as that first image of a black hole and the discovery of an ancient impact crater hidden beneath Greenland's ice. Citizens are signing up to actively participate in collecting data and working with you. At the same time, they see what is happening in their communities. They have seen and felt the air, water, and land qualities change. The public knows that the world's environment is changing, and they also know we have the knowledge and ability to work with them and be responsible stewards of our home planet. As we conclude this year's fall meeting, there are 3 key opportunities for every single one of us in our community as we look ahead to the next 100 years of our science. First, we must keep up our momentum. We still have much to learn and understand about our Earth and other planetary systems. We have allies who want to work with us. That's why Earth and space science is the science of the 21st century. Science, especially your science, is integral to humanity's future. Your work is vital to improving the health of our planet. Second, we must usher in a new era of responsible science. We, as AGU, must act with ethics and integrity and continue fostering scientific cooperation across the globe. We, the AGU community, must build upon our successes and expand our work to empower communities and inform policy decisions. When your work as scientists transcends both disciplinary and national boundaries, everyone benefits. People around the world are counting on us to help them understand what is happening and how we collectively can affect change on a global scale. We've done this before. The International Geophysical Year spurred action that led to the signing of the Antarctic Treaty of 1959, prohibiting the testing of nuclear weapons on the continent. It was also the dawn of the space age that has proven to be crucial for the Earth and space sciences. Scientists from the US and Mexico collaborated on a study about chlorofluorocarbons, or CFCs, that were harming Earth's atmospheres. Their work influenced the adoption of the Montreal Protocol to preserve the ozone layer. Scientists, policymakers, and concerned citizens spurred a cooperative effort known as the Convention on Air Pollution 40 years ago. This international agreement was established to protect both human health and the environment. These scientists embodied responsibility and showed how science can bring understanding and new knowledge while also positively influencing policy. Finally, every single one of us today needs to make a promise to ourselves, our colleagues, our institutions, and our communities that we will champion a new generation of responsible science and scientists. We have to make science welcoming and free from bias, harassment, and discrimination. We need the diversity of the best and brightest minds to come together, to be curious, to question and usher in new insights and new solutions for the benefit of humanity. Together, we can use the past achievements as a launch pad for our future. Together, we can become more engaged than ever before. When science is trusted, solutions abound. When science is trusted, hope is instilled for the future. Scientists have made great progress for the people and the planet. They have also taught us the most important lessons. We do our best by working together. We do our best when we empower science and empower communities. Together, we can spark change. So I challenge you to take the pledge by raising your hand or standing up right now to show you are inspired to act in 2020 to kick off the next century of Earth and space science. Will you join me and stand up and champion responsible science? Will you join me and stand up to usher in a new era of discovery and solutions for this Earth and the planets beyond us? Will you stand up that you are committed for diversity and inclusion and global collaboration, and that you will continue to advocate for the truth? As we heard, yeah. And will you stand up that we will do better, as we heard from former Governor Jerry Brown, to just persevere and say it over and over and over again. Our science matters, and it matters for the future of our planet and for humanity and for biodiversity. And what are we waiting for? Let's get going, okay? And let's usher in that next era of science. I'll be with you. Thank you. Safe travels, and we're counting on you. Congratulations. Happy birthday, AGU!